Okay, so let's open it up to any other questions about any of the projects, any of the homework, any of the topics. No questions? Oh, yeah. The format of the final will have 10 multiple choice, 10 kind of open-ended short answer things. It'll just reflect what your homework is. So we'll do a review today of all the homeworks. Next time I'll give you a better sense of what's actually going to be on the final. But if you've done all the homeworks, you're familiar with all the projects, you should have no problem. Other questions? No questions? Yeah.
Will there be any solutions posted for the homeworks?
For the homeworks. I wasn't planning on it, but
We just never got any feedback on it.
oh yeah, you never got any feedback on the homeworks. Let's see. So how about instead I give you the example problems for the final with answers to those, rather than all the homeworks. How does that sound? Okay. Deal. Well, what do I get? I didn't know it was a deal. Okay, so I'll get that to you by sometime over the break, before next Tuesday. And then on Tuesday, we can study that more specifically. Questions? This may be a short class. Yeah.
At the last two homeworks, the very last homeworks, we have to do the 32, 3, 4. Is that it? No 25?
Right. Well, there are 25 homeworks. Just they. Oh, no, yeah. Yeah, that's it. That's it. Yeah, I guess there's no 25. I miscounted. Yeah, right. Yeah, so you'll still get, then it'll be 19 out of 20, so it'll be a little more than one point each. Sorry about that. Must have miscounted. Oh well. Other questions? These are all kind of, yeah.
So you're gonna type out the example and the solution for it?
Yeah. Yeah. Yeah.
Is there an ETA on the secret sample?
The secret test cases for all of the projects, or for project 4? So there were some released, but they were buggy. Just asked the graders to review them. So I guess they are here. They are all up here, but some of them are wrong, or just not part of the language, like these, where there's multiple return statements. Yeah. Some of them have been updated, so I'm waiting on the graders to do this. If it takes too long, I'll do it myself. But yeah. Other questions on this? Yeah.
Where will there be coding on?
Coding? Well, yeah, you'll have to write code. So if I say, take this simple C program and write the equivalent LLVM. So it doesn't have to be perfect.
Okay.
It doesn't have to be perfect, but you can bring your notes. It's totally open note. Bring any notes you want. Yeah. Yeah. What day is the final? That's a good question. That's an important one. Yeah, that's in the syllabus. So this is it here. So they allocated 2.5 hours, but let's just get out of here by 9. The test should not take, hopefully it won't have to take you 2 hours. But you're free to take 2 hours if you want. Or what does it say? Oh, hour and a half, sorry. Hour and a half. Yeah.
By open note, do you mean electronic? Or you have to
Nothing electronic, because this is too easy to do communication. And
sure.
so anything on paper, even though it's probably going to kill a bunch of trees, but make your notes concise. Or remove the Wi-Fi chip from your devices and show me that you did it.
Wow, that'll be bad.
I'm just kidding.
There's the freaking Wi-Fi anyways.
Good point.
You're not wrong.
It's over here.
Yeah, I think it's in here. So yeah, I think it's just in the room. I think so. Yeah. Yeah, that would be rough. So yeah, I experienced this last year. I didn't know they don't actually tell you when you look up the exam time, but kind of makes sense that it would be here because nothing else is scheduled here, right? On that day.
Find them not in the same classroom unless it was one of those weird ones where you had like subsections all together.
Yeah.
Oh, right.
Yeah, calculus.
Yeah.
Okay. Other questions on like the content? Did anybody bring homework that they just had like questions about? Because I know you didn't get. I guess the labs were supposed to give you some feedback on the homeworks, but any ones that were sort of because the homeworks really are the review questions for the final. I'm just going to use those, or me and the graders are going to use those to just make questions. Okay, so we just go over some homework questions. All right. Submitting your project on GitHub. Anybody want to review that? No, just kidding. Compiling and running LVM. All right, hand compile a simple C program. So this was from Project Zero. What questions do you have about the, this is kind of small. What questions do you have about turning this into LLVM? Why don't we quickly go through, yeah, question? So what does the LLVM operation look like for, what's the LLVM operation look like for arithmetic? Call it out. So yeah, the operation is going to be add. It's going to be the type. It's going to be some parameters. So in this case, if it's, what's that? It's 9922.
That's stored in.
And right, you have to store it in a temporary register. That's it for the first one. What about for the next one? Print 102 divided by 2. What's that going to look like? So sdiv. Oh yeah, good point. Good call. Good catch. So yeah, assume this is the output of your compiler. You don't have to memorize the exact syntax. Just get it approximately right. Even if you miss some types or anything. I mean, I can't write this by hand either. I mean, this is not really meant for humans to write. But just get the idea. It's basically intermediate code. If you can write something that looks like intermediate pseudocode, no control structures, no nested stuff, single, signing each register once, then that's fine. So it's going to print integer, and what's it going to print? T1 gets printed. Okay, and what about this division here? So there's going to be some sdiv, new register. It's got to be a new register because you can only assign registers once in LVM. There's some data type. It's same idea. Oops. Oh, sorry. I'm sorry. Swapped in my eyes swapped, but yeah. So it's just going to be some sdiv expression like that, and then of course the print, or I think it's a call instruction. See, I don't even remember what this is, but if you get it, approximately right, it'll. And I think you need to put the type of it, which is something like that. Oh no, it returns a void. Yeah. Anyway, so I don't remember the exact syntax, but get it approximately right, and that's totally fine. Very lenient on this kind of stuff. If I can't do it, I don't expect you to do it. All right. Questions on that? So those are months ago, the basic LLVM stuff. Let's see what we got here. Lex and compile simple C program by hand. So you should just be aware of what the fancy term, the lexical specification of language is. It's just basically the words. What are the tokens here? So if I look at this line, how many tokens are there here? 3 tokens? 4,
Or 5.
5, 6, 5. Right, there's 5. So what are they? Print 99 plus 22. Yeah, exactly right. Yeah, so just be aware of the, what's a token, what's not a token. If we look at a one of these programs here, if we have this highlighted section, how many tokens are there here? Who says 6? Who says 7? All right, let's see. We've got if. The if keyword is 1 token. The left parenthesis is 1 token. X is 1 identifier token. 1 greater than operator token. 1 Y token. 1 rparen token, and 1 L curly brace. So what's that? 7?
7.
But yeah, just be aware those are the tokens. I didn't give you like specific names for them. So you might do something like circle the tokens in this,
Yeah.
something like that. Oops.
No. Well, yeah,
Okay, so that's tokenization. So some of the stuff that might be a little trickier is the regular expressions and the automata. You might need a little review on that.
Yeah.
So if we take like, all right, well, shall we go through it? Shall we do this example, or do you want a different example? Different example? Okay. Let's make a new example. Okay, let's come up with something. Let's try to make it comprehensive, but not too long to do. Okay, let's do this regular expression. How's that? Is that complex enough? Is that more complicated? Say again? Will this be on the final? I am not trying to trick you. I want it to be like very straightforward, very simple. If I can't do it, then you should not have to do it. The bar?
like what they all.
Oh yeah. Oh right. The operators. Okay, so what are the minimum number of operators you need for regular expressions to describe all possible regular languages? Yeah, there's 3. And what are they?
Concatenation, operation, and closure.
Right, so there's concatenation, alternation, and closure, or clean star, or clean closure. All right, and what do they mean intuitively? So what does some language followed by another language, what does concatenation mean? You recognize one language first, and then you recognize the other language. So so in this scenario, A and B look like they're just characters in the language. But if I have a language L defined to be all of the strings described by this regular expression, then I can also apply the operators to the entire language. So if I have some other language G, then I can concatenate the language L and G. So say I want to find, I want to match country codes and then followed by phone numbers. So what do? I just first match country codes and then I match the line number or the phone numbers. So it's not super complicated. It's just this letter follows all of the letters in this line, all the strings in this language are followed by all the strings in the language after it. Okay, what about alternation? It's like an or, yeah. So if I have one language for, say, all of the numbers in my, so I'm going to use some kind of non-standard syntax here, but if I have something describing integers, so I'm going to use, plus is the clean plus, it's one or more. And I've got something for identifiers, which is, maybe A through Z, or 0 through 9, plus, then I can say I want to see either a digit, an integer or an identifier, but not both. Of course, this language actually subsumes the other language, so this actually equals that, but minor points. But anyway, the point is you read one or the other. All right, what about closure? Closure is the slightly more complicated one to reason about. If I've got, well, let's just take our example language. If I've got this example language here, what are the possible strings in this language? So what's one possible string in this language? Yeah. D, A, and some number of A's. Actually, any number of A's. So that means D is in the language, DA is in the language, DAA is in the language, DAA is in the language, and so on. Those are all strings that are in this language that match this regular expression. What's another example? Yeah. Just D, right? So I have that here. What else? So D, BC, BC, or D, BC, or D, BC, BC, BC. These letters are losing their meaning as I say them over and over. But then with alternation, I can also have BC followed by A, BC followed by BC followed by A followed by BC. So any combination of A followed any combination of A or BC, all concatenated together. That's what clean star does. And for your compiler in the compiler world, if you want to match an arbitrarily long integer, well, you don't want to have to specify every possible integer you can recognize. You want to have this nice compact language to specify a potentially infinite set of possible strings that you want to match. Or even if it's just a very large set of possible strings. Regular expressions can make that convenient. All right, questions on that? Questions on regular expressions? So this and the grammars are probably the most conceptually technical parts. But I'll give you fairly straightforward problems like this one here. So let's look at turning this into a non-deterministic finite automata, which is just a fancy term for a state machine. So what are the elements in a state machine? There's a formal description of it, but kind of informally, how do you define a state machine, a finite state machine? Anybody remember? Yeah.
You have a start state and then end state.
Good. You got a start state. So diagrammatically, we use just an in-edge arrow. And we have some final state or final states. There can be multiple. And that is represented with a double circle. Okay, what else do we have? Yeah. Right, you've got transitions between states. So for instance, so you can think of finite state machines in one sense as being a recognition engine, kind of like classic AI. How can I have a machine that can recognize some pattern? I have to define what that pattern is by building the machine, but in a sense, this is like the classical AI, before all this deep learning stuff. And the way we define it, we say, well, the machine is in some kind of state. In practice, we can represent that with a state number or with a graph node. And when the state machine sees a new symbol in the input, like the symbol D, it transitions to another state. That transition could make it stay in the same state. It could transition to 2 possible states or 3 states because it's non-deterministic. But yeah, there's a set of these edges diagrammatically represented as edges of these transitions on inputs, on symbols in the language. or symbols in the alphabet, sorry. Okay, so that's transitions. We've got states. We've got a starting state. We have an ending state. What else? Anything else? Yeah. Right, yeah, a set of all the states. Good, yeah. So the edges are the transitions in the diagram form, and the circles are the states. So it's a finite state machine, so you've got a finite set of states, which means you have a finite set of edges. And what about the alphabet? The alphabet is also finite. Actually, that's why you have a finite set of edges, because you have a finite set of states, finite alphabet. So you have a finite set of edges between those. Okay, and that's the full specification of an NFA or a DFA, non-deterministic finite automaton versus deterministic. So what's the difference between NFA and DFA? Yeah.
An NFA can be in multiple states at once.
Yeah. Yeah, exactly right. So the specifications of them are nearly identical, except in the DFA, one transition goes to, or one symbol takes you only to one state. Whereas in a non-deterministic finite automata, you can have multiple transitions from the same symbol and the same state. So this would be a DFA. This would be an NFA. What about this? Is this a DFA or an NFA? Huh? What's that? What I have pictured. If I have, say I have this. Is this an NFA or a DFA? Who says NFA? Who says DFA? Ah, okay. Sorry, so I tricked you because all DFAs are NFAs. Because so that was sorry if I didn't plan that to be so tricky, but so yeah, an NFA can be in multiple states at the same time, but it can be. It doesn't have to be. So all DFAs are NFAs. Just yeah, they're all finite automata except the DFA is a type of automaton where you've got a restriction on the number of transitions for a state and a symbol. When is it exclusively just one? DFA. Well, we can go through it. We can go through it. Okay, I'll give a small example. Let's see. Well, we'll see the difference when we do the transition. It's sort of a, I can't think of one up on the spot. I mean, I guess we could do something like, would this work? A star followed by A. Oh, okay. I think I can give you a simple one. So let's say I've got A, B, or A, C. So the NFA version of an easy way to translate this into an NFA is there's a couple ways to do it. You could have two transitions from A, from the initial state, and that goes to a state where you have a transition on B and C. And then these are the accept states. Another way to do that, and another property that NFAs have, is you can use this epsilon symbol to mean no characters were recognized, but you still move to other states. So I could also draw this an NFA for the same regular expression like this. Questions so far? Questions? All right, so that's kind of the major differences. You should sort of know kind of conceptually, what's the difference between the two, that all DFAs are NFAs. Okay. So let's talk about how we generate, how we take a regular expression and convert it into an NFA. So it's actually easier to convert it into an NFA than it is into a DFA. That's why we go through it first. Even though NFAs are sort of harder to reason about, it's harder to reason about having multiple states at the same time. It's much easier to translate a regular expression into it. All right, so who remembers how we do this? How do we go from regular expression to non-deterministic finite automaton? Say again? Yes. Well, eventually, yeah, it's all going to end up as arrows to states. So I didn't cover this too rigorously, but the idea is that this regular expression can be turned into an expression tree. So I sort of had you do it without drawing the explicit expression tree, but you could certainly draw this as just like you've done with, because we talked about this before we talked about parsing, but now that you know about parsing, this is just a different kind of expression that has its nested structure. So we can turn this into an expression tree. So there is some operator precedence in these regular expressions, in the regular expression language. The concatenation is highest precedence. I mean, it's basically like multiplication, addition, or addition, multiplication, and exponentiation. So you can think of OR as being like plus, concatenation as being like multiplication, and clean star is kind of like being an exponent. And parentheses, enforce, explicitly make the order of operations. So this is the kind of first operation. It's the lowest in the tree. And then this language that's constructed here is operated on with alternation. So A or this language, that's this part of the tree here. And then closure is just a unary operator. So that's closure. And then finally, the top level concatenation, which is here. Make sense? Did I make any mistakes on this? Does it seem right? And so I had you sort of just remember the order of operations because everybody you were sort of indoctrinated with order of operations in arithmetic. And now that you know that that's just sort of an arbitrary made up rule, right? Because you as the language designer actually implemented that, it doesn't exist in nature somewhere. It's some rule that humans made up. But because you were, inculcated with that, I could use that to tell you what convey to you what the order of these operations are, and you could just follow those in order to generate the NFA. But if you were to do this automatically, you could actually write a parser for regular expressions and a code generator that instead of generating code generates a DFA or an NFA rather. So, okay, anyway, little digression. All right, so the way we do this conversion into an NFA is to just do a post-order traversal of this tree and do the same kind of code generation that we did for simple C. So this concatenation, and the way it works is we follow those templates, and I may have to look at those again if I forget what these are, but we follow those templates that we saw in the Dragon book. So concatenation looks like this. And then if we combine that with alternation, or actually, I'm sorry. I forgot about the individual symbols themselves look like this. So if I've got C and B, I join, should I show the templates? Do you guys want to see the templates again? I think that might be helpful to see the templates. Let me find those. So they all just kind of fit together. So the starting state of the second part of the concatenation, the right operand, is the ending state of the left operand. So if I've got my example here, this is what, I don't know if I showed you what it looks like for just a single symbol, but Oh yeah, so a single symbol just looks like this. If you're just recognizing one symbol, right? We saw that with D. So if I've got two of those, then I take this, which is the ending state of the B recognizer, and I make it the beginning state of the C recognizer, and voila, I've got concatenation. Questions on this? Questions on this? Maybe a more interesting way of looking at it is we've got our two pieces here, and we connect them together like Lego blocks. Okay, and similarly, we've got this symbol A. So this is our post-order traversal of the tree. So we just traversed this part. Now we finish this node. We finished this node, we finished this node, and now we need to implement the alternation. So the alternation pattern looked like this. And as all of you realized, or many of you realized, that you could sort of hand code an NFA yourself or a DFA that matched the regular expression that used fewer states. But if you're lazy like me, then you want to mechanize this and not have to think about it and just think about the operation of mechanizing it. So I just use this template just sort of blindly. Because if I know that it's the same thing when doing recursion. When you tried to reason about multiple recursive calls, it's a massive pain. But instead, if you just think about one recursive call at a time and how they fit together, eases the burden, eases your cognitive burden. So you can think about other things. Okay, so to do alternation, we take our two alternates and we connect them as seen here. We create a new initial state and a new final state and point those using an epsilon transition to the beginnings of our beginnings and end from the ends of our alternates. So I wrote something totally wrong here. Okay, so here's our new initial state. That looks like a double state. They have epsilon transitions. Okay, so we've done our post-order traversal. We finished this node. We finished this node. Now we're at the closure operation. So what does closure look like? It has this structure. So whatever our NFA, our sub NFA inside is, we make an epsilon transition from the end state to beginning state, and we have these extra states so that we can have the zero case. So that's the only reason we have these here. We have this extra states here just so we can handle zero instances of this sub language or this sub NFA. Questions on this? Make sense? Make sense? So let me design that structure. Here's our initial and end states for handling zero instances. Here's our transition into our sub DFA. And here is that back edge for repeating over and over this sub NFA. So you can see that kind of inside here was our alternation node here. That was our alternation. Questions? Yeah? Yeah.
Where does D go?
Yeah, okay. So we, as your classmate pointed out, we finished this node, but we still got this node to work on. So I didn't show it, but when we process D, just as before, we've got this, what am I doing? We've got this sub NFA that handles D. And so with concatenation, all we do is we take the two pieces and just bring the initial state of one to the final state of the other. Let me make some room for this. So we take the final state of the left operand and marry it with the initial state of the right operand. So what about the accepting state? So you would just update the accepting state to whatever, the next, in the template they show each time you make a sub NFA, it has a built-in accepting state. And so whenever you modify this, or whenever you have a transition away from this, it's no longer the accepting state necessarily. But anyway, kind of a minor technicality. And same with the starting state. So in all these cases, the sub expression has its own starting state, and as soon as that's replaced with something else, that's no longer the starting state. But minor technicality. Bless you. Other questions on this? Okay. So yeah, so I'll give you some regular expression and ask you to draw an NFA for it. But it won't be super complicated. Okay. All right, let's see. How am I on time? Oh, we got plenty of time. That was homework 5. Homework 6 was NFA to DFA. This was a fun one. Who remembers this? Does anyone remember this? Okay. So let's walk through that. Let's walk through that on this same problem, and see if I actually remember it. Let's see. How can I think I need to copy this. Can I copy it? Okay, I can't. All right, I'm going to delete all this other stuff. All good? Anybody? Yeah, okay. So here is our DFA or our NFA, and we can construct a DFA from it using the subset construction algorithm. All right, who remembers any of the steps of this? So the first thing we need is to number these states. That'll help us. Yeah, this long process. Yeah. That's right, yeah. So the first thing you need to do, first thing we need to know the starting state. So 1 is our starting state. And we want to construct the first thing we need to do is we need to construct the epsilon closure, which is just if we've got some state. Oh, I forgot to add the epsilons here. So if we've got some state where the next state from it can be transitioned just with an epsilon, then we take all the states that basically can be reached from that state. So if we're on state 1, what's the epsilon closure of state 1? Just 1. There's no other states that we can get to without us consuming a character from the input. And then we just go through the entire alphabet. So in this case, our whole alphabet is A, B, C, D. And we just go over each character and see what the next possible states could be. So for A, what's the next state from state 1? There is none. So, this is like empty set. You can just assume, so we'll just assume that for any blank entries that there's no transitions. For B, same empty set. C, same as empty set. And then we've got state 2. That's the next state when you transition using D from state 1. If we take the epsilon closure, we see that there are all of these many states that follow via epsilon closure. So the epsilon closure of 2 includes all those states. 3, 4, 7, and 10. This is very easy to make a mistake. So as an aside, if you can just figure out a DFA for the regular expression, by all means do that. You don't have to do it this way. This is like the rigorous way to do it, and how this is the algorithm, how a machine could be implemented to do it. So that's our transition for D. And then that gives us a new state in our DFA. So our new state in our DFA is, well, let me just, yeah, we'll do it this way. Actually, let me move this down here so it'll be a little easier. So this is my new state that I've just found. And I'll call this state B. I'll call one state A. So state A transitions to state B when it receives the input D. So I did sort of a lot of fast stuff there. Questions on that? Questions on any of that? Okay. All right, so if we're in state B, so this is our DFA state. These are our NFA subsets of states. If we're in state B, what symbols can we transition on if we're in state B? Yeah, so we can transition, well, three only transitions on to epsilon, so we've covered those transitions in our subset construction. So if we're in state B, that means we're simultaneously in these 5 states. So that means if we transition on A, this one can't, this one can't, this one can't, this one can, it transitions to 8, and 10 can't transition on A. So the only state that we can transition to on A is state 8. If we take the epsilon closure, that gives us 9, gives us 3, 4, 7. That is yet another subset construction that we can relabel C. Same thing for B. We get a new state D, which has 5, and that's it. Questions? So yeah.
Would you also put 10 in that?
E probably. Let's see. C.
9.
Where was not? Oh yeah, you're right. Yep, 10 is also here. Sorry about that. Yeah. Okay, so I think I'm already making mistakes, so I think that's enough review of this. Other questions on this before we move on to the next thing? So the regular expressions I'm going to give you are probably simple enough to just figure out what the DFA is. By all means do that, that's fine. I'm not going to say you have to do the subset construction. It's a kind of a tedious algorithm. Yeah.
Have to go from DFA to regular expression, right?
Those are actually fun questions, but do you want a question like that? No? All right. Okay, so no question on DFA to regular expression. I'll not put that.
What would you be looking for in the final answer on something like this?
The DFA. Something that is a DFA. So it shouldn't have epsilon transitions in it because it's not a DFA if you're in multiple states at the same time. Yeah. Okay. All right. Other questions on? I think that covers the regular expression stuff. Just be aware that these automata are used to implement lexers, and that's actually how you implement tokenization. I'm not going to actually ask you to write code for that. So let's move on. So this is into grammars, context-free grammars, precedents, etc. Oops, it's the same one. So you should be, yeah, I mean, you can bring notes. So you can have access to all the simple C grammars. But you should just sort of be aware of how like operator precedence works, like the way to resolve it in a grammar. So let's review context-free grammars really quickly. All right, so just like a DFA or an NFA or any kind of automaton, there are some like properties that they all have. So what about context-free grammars? What are the properties that any context-free grammar will have? And in some sense, they're kind of similar. Yeah. Well, yeah, they're recognized by push-down automata. So maybe I should make my question more precise. If we're specifying a context-free grammar, what do we need to specify a context-free grammar? It is certainly true that yes, you can recognize a language in a context-free language using a push-down automaton. But if we want to write the grammar for a context-free language, what components do we need? In the DFA, we needed like a starting state, transitions, alphabet. What about for a context-free grammar? What does it look like? What does it have in it the representation of the grammar? So we have the grammar like here. Yeah. You got terminals and non-terminals. Good. Yeah, we got terminals and non-terminals. What else do we have? Starting symbol. So program by convention, it's the first non-terminal on the left-hand side. And what about this? What is the name of the thing that takes a non-terminal and expands it to a series of smaller symbols in the language or other symbols in the language? Production, yeah. Those four things. You have non-terminals and terminals. Those are your symbols in your language. And productions take non-terminals, which are like kind of ghost symbols of your language. They're not actually part of the utterance. They're not actually part of the string. And they just represent the structure using other symbols that represent the structure. So it's kind of a theory about how language works in the brain, that there are these kind of ghost symbols that can be used to compute the output of compute a sentence, produce a sentence by generating it from this grammar. So it's called the generative grammar. But anyway, we can use it for programming language specification. All right, so if we've got our grammar that has no, okay, so if our grammar looks like this for expressions, this kind of is a very simple way to describe the arithmetic expression grammar. Okay, maybe we should talk about like derivations first. So if I've got this string and I want to derive how my grammar generates this string, how do I apply this grammar in order to generate this string? So for simplicity, I'll just say E for expression. So how does this work? How do we use this grammar to generate or recognize this string? Yeah, it's like recursion. It's a kind of recursion, and in fact, these grammar structures, because as your classmate said, with a push-down automaton, that's the machine that will actually perform the recognition of those languages. So they are recursive. They are this like computational thing. And the way it works is we take, starting from the starting symbol, we apply. Well, let's start at expression to make this a little faster. If we're starting an expression, we apply each of these productions. We apply each of these productions, starting from the starting production. We apply each of these little transformations from the starting symbol. And so if we end up with E plus E, we need to find an expansion or a derivation of E that's going to lead us to the utterance in our language. And so looking at the productions in our language, we've got expression goes to number. So that is probably what's going to be, oops. Wow, I lost it. Okay. That's probably going to be the next production in our language. It's going to be, it's going to be number. Plus E, and then we do another derivation, or another step in the derivation, and E again gets replaced with number. Make sense? Mostly review, right? And if you're a more sort of graphical person or a visual person, you could represent this as a syntax tree. So E goes to E plus E. E expands to a number, and I'll just write the token directly. What did I have before? 10. 10 plus 2. So that's where you get these parse trees from, or these syntax trees. And the whole recursive nature of these languages shows up when we've got nested structures. So if we've got 10 plus 2 times 3, well, there's no production in our language that matches that pattern by applying one step of a derivation, by applying one rule in that grammar. So in order to derive this string, we have to exploit the nested structure of our grammar. So what would be the first step of this derivation from E, from expression? What's the first production that gets applied? So E times E? Anybody else have a difference about what it could be? Yeah.
Expression plus expression.
Could be expression plus expression. So who says E times E? Who says E plus E? Who says either? Okay, why is it either?
Because it doesn't have any order, it doesn't have any preference, right?
Yeah, it doesn't. There's no precedence here because both possible derivations are possible. So what is that grammar called? What is the grammar called if you have multiple derivations of the same? It's an ambiguous grammar. Yeah, exactly. It's ambiguous because the same string can have multiple different derivations. More precisely, multiple different leftmost or rightmost derivations. What? Oh. Okay, so let's pick one. Should we do plus or multiplication? Call it out. Multiplication? All right, so if our first step is the multiplication production, then this multiplication must eventually must match this terminal. We've seen a terminal. This is the terminal we've seen. Okay, so if we're doing a leftmost derivation, what happens here at this E? What's the next production that gets reduced here? E plus E, right? It has to be plus because there's only, if we did E times E or any of the other ones, we would either run out of terminals or we wouldn't be able to match terminals. We've already matched this multiplication, so everything before it must have a plus in it. Okay, and so these E's match numbers, and this gives us one derivation of this tree. So turning to the semantics of these arithmetic operations, which you guys implemented, these symbols are just symbols. The machine does not understand what a ASCII 10 is or what an ASCII plus symbol is. Has no comprehension of that. The compiler takes that and translates it into machine code, which ascribes semantics to this parse tree. So in the semantics of our language, in Simple C and other programming languages, what is the meaning of this? What is the meaning of this expression? Or how can we evaluate this expression? Or how can we generate code for it? Any answer will suffice. So how can we just define the meaning of this? So what would it look like in LLVM, this? Or in what would it look like in intermediate code when we do this? What's that? Yeah, you follow the grammar. So we do that operation, those operations that we do this post-order traversal, right? So when we go to emit the code for E, we first have to emit the code for the left operand in order to know what temporary register that value is going to be stored in. And when we do that, we notice that this is an expression that itself needs to be evaluated. So in order to evaluate this, we have to evaluate the left side and the right side. Those are just constants. So to use a kind of simplified intermediate code, this is not like correct LLVM, but we'd have some temporary register 1 that equals 10. So this is E here. Some temporary register 2 that equals 2. Some temporary register 3 that equals T1 plus T2. And finally, we have the left operand of our parent E. So we can go on to compute the right operand. And just like before, this gives us a new temporary variable 4 that equals 3. And finally, we can compute or generate the code for our top level expression, which equals T3 times T4. So that's like the meaning of this. If we were to compute this, actually run this program, what will we get? It's a little tricky, right? Your indoctrination in math classes is compelling you to give the wrong answer, right?
36, right?
Actually, I don't know. Yes, 36. So notice that this is computed first, and then the result is computed. So even though there's no parentheses here, because of the derivation we chose, and because of this post-order definition of the evaluation of this tree, we get 12 times 3, which is 36. And that's because this grammar was ambiguous. Either derivation was possible. So how do we resolve this ambiguity? Using the grammar. Hopefully everyone knows this now or has struggled with it in their compiler. Yeah. You introduce extra non-terminals to force the derivation to first try to derive plus and minus. Because as we saw in this grammar, whichever operation was derived first, that was the operation that happens last. Because we define the meaning of this tree as a post-order traversal of it, so that the stuff higher in the tree happens last. So in that, okay, so what did that operator precedence grammar look like? So instead of instead of this, E plus E, what extra non-terminals did we add? Well, that was for like right recursion elimination, but let's do the simpler one first, the left recursive version, because the right recursion one's a little bit more complicated. Yeah. Yeah, we added term and factor non-terminals. And so what did the expression look like? So what operations do we want to derive first? Or what are the lowest precedence operations that we wanted to encode? Plus and minus. So we had plus t or e minus t. And for term, what operations do we want to encode? There are multiplication and division. And in factor, you could either have a number, or if you wanted to have parentheses, we could add a new, well, parentheses are ultra confusing, so I'm going to write this out. Because parentheses are sometimes part of the meta. Oh, sorry about that.
There we go.
Oh, sorry. So yeah, we had two new non-terminals, term and factor, representing term and factor. The expression has to derive pluses and minuses first, thereby putting them higher in the tree. Term derives multiplication and division, and then factor can either be a number, or in the case of our language, if we wanted to allow parentheses, we have a left paren terminal, followed by E, followed by a right paren terminal. And so parentheses are ultra confusing when you're describing these languages, because the parenthesis might be part of the language you're trying to process, or it can be part of the language, your meta language. So, and this is just by definition. You just have to choose this and get around this. It's kind of actually, this is a problem in who's heard of SQL injection attacks? Oh, good. Okay, you heard of SQL injection attacks. So this is a problem this is a difference. Well, Yeah, this is kind of a difference between the meta language and the language like you're trying to process. So how does a SQL injection attack work? Does anybody want to tell me how this works? Yeah.
Like when you're filling out like a form, that will be put in like a SQL query,
Yeah.
like create something in the database.
Yeah, so it allows you to kind of do arbitrary SQL database operations through a form field. And that's because when the simplest way to program that is like take whatever the user, whatever string they put in, and just like literally do string concatenation with whatever they put in, plus some SQL query, and then run that whole query. The problem is the input language that you allow the attacker to put in doesn't have the same kind of meta symbols. So a little tick mark or a quotation mark is totally valid in the input language because the input language is just all ASCII characters. But in the SQL language, that quotation mark has meaning. It's not part of, maybe it was being plugged into like a where query. This is database stuff, but in a SQL database might say, give me all fields that have this user's password, so I can get the password out. And so implicitly, the developer's thinking, well, this field is only meant to have data inside of a string for the SQL query. But if you allow arbitrary ASCII symbols in, and you just concatenate this whole string together, well, that quote has meaning now to that SQL expression. So I think maybe seeing an example is maybe better. So if you try to construct, so this is what a query looks like in SQL. So this is not, well, oh yeah, so here's a case here. So you're trying to construct a query, and you can see that, what do these quotes mean? It depends on there's multiple languages being mixed here. So in my outer language, this is actually where compilers sort of helps, because in compilers, it's very easy to get confused between the source language, which in this case is, well, the source language is SQL. The language you're writing the compiler in, which in this case is whatever this is, I don't know, this is PHP or something, I guess. And the output language, although this is not a compiler, this is like sort of an interpreter. But the output language is also like kind of SQL. And so these quotes have different meanings in these different languages. So this single quote is in the PHP language. This double quote is in the SQL language. And the attacker is the developer is assuming that the attacker is not playing with, not giving symbols in any of these languages. They're just assuming that the language input by the user is, not using any of the target language, the SQL language. And so if I put in a quote mark here, then this quote in my target language, the SQL language, will be closed. And then I can put whatever, SQL command I want. Actually, I think XKCD has the, oh yeah, Bobby tables, that was it. So this is the, oh, where is it? Oh yeah, so this was, yeah, so this is, the joke was that somebody named their child this, so that when they, wrote their name into the database, it would like delete all the data about students. Anyway, you can look it up. SKCD. Good if you want to be, very nerdy. Anyway, so that's a little aside. So this compiler stuff, it actually pops up everywhere in computing. You see this all the time. The difference between the source language, the target language, and the meta language that you're describing your operations in, and that's all kind of at play here. Okay. Anyway. Okay, so that's how we handled operator precedence. Questions on that? Questions on operator precedence? Yeah.
Do you have to include like the epsilon equivalents for these?
So the epsilon stuff was when we converted it to write recursion. If you remember, so in write recursion we turned E into the right recursive version, and there's basically just a template, and I can barely even remember what this looks like. So it was TE prime and then E prime. God, what was it? Yeah, something like this. So it turned this left recursion into right recursion. But I'm not going to make you do that because that is kind of a pain to do. And it's just, you just look up a template in the Dragon book and it tells you how to do it. So not super interesting. I mean, as long as you sort of understand that left recursion doesn't work with recursive descent, right recursion does, so you got to change the grammar. Okay. Any questions so far? Other questions? What time is it? All right. So that's pretty good. We're sort of halfway through the homework. Yeah. Okay. Other questions? Other questions? So we kind of covered arithmetic expressions. You should sort of understand recursive descent. I guess just real quick. So how do we turn this? If we've got this right recursive grammar here, how do we turn that into a recursive descent parser? What's the kind of general schema for taking a grammar and turning it into a set of recursive functions? Huh? Is that kind of too arbitrary a question? So if I'm writing these two productions as in a recursive descent parser, what does my code look like?
Oh, like the actual like code.
Yeah, what does the code look like? Yeah, so you've got a function for each non-terminal, and the body of that function, more or less, is the right-hand side of that production. So this would call the T function, followed by the E prime function, and E prime would match. So if it's a non-terminal, you match it, consume an input, consume a token from the input, and then call whatever non-terminals. So non-terminals become functions. Terminals become consuming a token from the input. That's the basic schema. So I'm not going to ask you to do too much with that. Just be aware of that. And that covers, LR parsing. I won't ask you about LR parsing. That is pretty tedious to walk through. And, it's meant for a computer to do, not for a human. All right. And then, so next time we'll review all the, variables, type checking, and the, the more fun code generation stuff. Okay. So have a good break, everybody. I think this is the last class of the week, right? So, all right, everybody, have a good one.